All right, we have reached the last layer, people, of the TCP/IP stack, where we talk about data link and specifically the protocol ARP, and then we put everything together. There are two discrete services that the link layer offers. One is framing, and you will hear that the datagram now it's called Ethernet frame. And the packet format is interesting, the header format, because there's a header and a trailer, so that's pretty interesting. And there's MAC addresses that are characterized by hardware, and they're not the same as IP addresses. The second service is reliable delivery between nodes. So we did this indeed already in the TCP protocol layer 4. However, this is a service that is offered in the link layer as well. It's not used as often. And for wireless links, the link layer tries to take care of the reliable delivery because there are higher rates and error checking and all of these good things. So a question in the slide is why should you have both link level and end-to-end reliability? A good question to be on the quiz. More link layer services, flow control, error detection, error correction, and half duplex, full duplex. So the flow control, how can we pace between nodes and not have any issues with losing information? Error detection and correction are quite self-explanatory. And full duplex is something that you already know that an Ethernet cable, for example, does not transmit information only to one direction, but full two directions. And of course, wireless works the same way. An interesting question over here, people. Where is this link layer implemented? Is it the operating system like the rest of the stack? Or is it the hardware, because we're getting closer to the hardware? Well, kind of both. But mainly, as you see in the slide, is the network interface card. So the NIC that you may have heard before, that is in your computer, and the wireless card, of course, that you have in your computer. So, as you can see, the link layer is both parts software and hardware in this very nice picture. And and furthermore, it includes firmware. So it's very interesting that it crosses three different layers: software, firmware, hardware. Another interesting thing that we have already discussed quite a lot is a switch. We talked about layer 3 switches that are called routers in the previous lectures, but here we have layer 2 switches, and you see one of those. They look very similar, and the operation is similar, but the layer 2 switch goes up to layer 2. It doesn't implement any networking, and it only connects devices that are in the same subnet. So here in this picture you can see some IoT, some webcams, or some computers, phones, and all that good stuff. So keep that in mind. A layer 2 switch connects only a single subnet, not multiple subnets. If it's multiple networks, then it's a router. This idea about multiple access, because multiple computers access one medium, such as the cable, the Ethernet cable, or the connections that are corresponding to that link layer, the cables, fibers, etc. And then of course the wireless medium. The idea of multiple access is a very interesting one, and there's lots of protocols related to it. We're not going to get into too much details, but to know the ideal multiple access protocol, given a broadcast channel, you want to have no collisions, and the average rate of the channel for each node, if there's m nodes, and the total rate of the channel is r, should be r divided by m. That means that you arbitrate perfectly. And then the multiple access protocol should be fully decentralized and simple. You don't want to have a central bottleneck telling you who is allowed to transmit next and use your channel, whether that's the air or a cable. And you do not want to have synchronization, and definitely you want to keep this simple. Multiple access protocols are Aloha, TDMA, FDMA, and CSMA-CD. Just some names and alphabet soup that you can study further if you take a computer networks class. The MAC protocol, multiple access protocols, have three flavors. The ones that divide the channel into smaller pieces, whether that's the wireless channel or the time or the whatever that is being shared, a frequency or something like that. This flavor is called channel partitioning, and then there's random access, where the channel is not divided and randomly clients access that channel. And then there's a taking turns channel that could be a round robin or whatever arbitration scheduling exists for this channel, and that's the third flavor of a multiple access protocol. We have already talked about IP addresses, but just so you know, when your computer connects to a LAN, there are two addresses and two interfaces, okay? Two hardware interfaces, literally, an interface on your computer and an interface on the switch or whatever you're connecting on or the router at your home network and all that. So the network layer address corresponds to an interface, this IP address, and it's used for layer 3. Network layer forwarding. The MAC address, which is the layer 2 address, in this case is different. As you can see in this slide, it looks different and is different, and its function is to be used locally to get the frame from one interface to another, the Ethernet frame, between physically connected interfaces, like connected through a switch, like we discussed a couple of slides ago. Same network, same subnet, and no other networks for MAC addresses, not different networks. The MAC address has 48 bits, and it's burned in the network interface card read-only memory, and also sometimes you can set it through software. The first 8 bytes correspond to the manufacturer of the network interface card. This could be Apple, Dell, and so on and so forth. So how does the poor switch know all these MAC addresses, and if only the IP addresses are known? So the switch, the layer 2 switch, has what we call an ARP table, ARP for address resolution protocol. And here's how this ARP protocol works. Let's say A wants to send a datagram to B. B's MAC address is not in A's ARP table. So A will broadcast an ARP query, and you may have seen this if you're sniffing. Yeah, I know you do sniff wireless networks, so don't play innocent with me. So you may have seen this ARP request, ARP broadcast message, because if it's broadcast, everybody can see it. So you may have seen the message that says, who has this IP address? So that's the query packet, and that contains B's IP address. And it says, who has B's IP address? And then the destination MAC address in this packet will be FFFF, all Fs, because we don't know it. And all nodes in the local area network will receive this ARP query. Now, when B receives this ARP query, because B knows its IP address, it will reply to A with its MAC address. And then the frame is sent to A's MAC address, and A's ARP table is updated. Actually, you can see your ARP tables if you're a super user. You can see the ARP tables by using a terminal command arp-n. So ARP now will cache, save the IP address pair, B's IP and its MAC address, and then, of course, eventually this information may time out because IPs change and all that. One thing to mention is that ARP is a plug-and-play protocol. The nodes create their ARP tables without intervention from an administrator. So each node can have an ARP table, and also the layer 2 switch has what we call CAM tables, switch tables, and they are similar to these ARP tables. So here you see two subnets trying to connect, and in this case, we have a router between those two subnets. So I want you to think, now that we're starting to put everything together, what will happen if A wants to talk to B in this case? Okay, again, ARP is going to happen, so think about all the steps that I mentioned in the previous slide, and then some routing is going to happen through the router. And in between, again, MAC addresses need to be learned. The router needs to learn the MAC address of B, and also if B wants to reply to A, the router has to learn the MAC address of A. So think about the steps that need to happen over here, where we also have a router in between. So I'm not going to give you all the details because it's a good thinking exercise. And of course, you can ask any questions you want on the quiz while you have the open question. Here we have this wonderful encapsulation picture where A creates an IP datagram with IP source A and destination IP B, and then A creates also a link layer frame with R's MAC address once it knows it, once it goes through all the steps that you thought through in the previous slide. And then the frame contains also B's the frame contains R's MAC address, because first the frame is going to get to R, and from there it's going to be routed to node B. Continuing further, the frame is sent from A to R, now that A knows R's MAC address and has a frame ready to rock and roll. And then the frame is received at R, and then the datagram is decapsulated so that the router R can decide to which interface it should forward that frame eventually. Notice that the router goes only up to layer 3, and of course it has no need to go higher than that. It doesn't implement higher than the layer. Now at this point, there's something interesting happening, because R needs to get the datagram with IP source destination, IP source A, destination IP B. So now it decides that it will create a link layer frame with B's MAC address because it knows it has it in its tables and all that. So B's MAC address is going to be the destination in that frame. And then this is going to be encapsulated. You also see the header and the trailer and sent to the proper interface. We're almost at the end. So at this point, R will forward the datagram with IP source A and destination B and towards its destination, which is the B host. And in this case, there may be a switch that will route the final frame to this host, or just a shared medium. And finally, B receives what A was trying to send to it through routing from one local area network to another one. In between, there was a router, and before that, there could be layer 2 switches or just interconnections, shared mediums. So these are all the steps that I told you to think about. I want you to really have these details in your head because there may be questions in the final or the quiz about the set of steps that you take to route something from one local area network to another. We're not going to say too much about the physical layer, which is about the mediums and the zeros and ones, and it's more physics than computer networks protocols. Here you can see even an optical fiber. I think the middle one is an optical fiber. So the physical layer is really the hardware layer, and there could be an additional class for signal processing and all that. I actually took one of these classes, very interesting one, that is the whole class on the physical layer. And just a taste and what this is, and we will move on to wrap up the computer networks knowledge. Wrapping up over here, we can see some topologies that you may encounter. So just so you know the names and what they look like: star topology, hosts connected through a switch. Actually, this is a router because then it connects you to the internet. Actually, think why this top left topology, I consider this a switch and not a router and not a switch. The ring topology, everyone is fully connected in a circle, the bus, the mesh, just a visual of different topologies that exist. All of these are maybe encountered in today's networks. At this point, it will be nice to put everything back together by talking a little bit about Wireshark, which you have been using for your Lab 6, which is due this week. So your Wireshark is really using a low-level operating system library called Packet Capture Pickup. In C, it's the lib pickup, SCAPI, the Python library wraps around that C library. And what Wireshark will show you is the TCP stack. The Wireshark will show you some application data because of the packet analyzer, and the pickup library will give you the transport layer, network layer, and link layer data, as well as physical. You may have already noticed that you see zeros and ones in your Wireshark capture. So you get the full stack of information with Wireshark, a very powerful tool. It receives Ethernet frames when it sniffs, and and then it dissects them and gives you a very nice visual. It also does statistics, Wireshark, and we will look into those. We will use Wireshark when we also do computer network security. So this will be a tool that we will use quite extensively. To recap, Layer 2, there's several services that Layer 2 offers: error detection and correction, multiple access, and link layer addressing. It's also instantiates multiple different technologies like Ethernet, MPLS, local area networks, etc. And then my suggestion here is to put everything together now that we have looked at all the layers of the TCP/IP stack. I would recommend to you to go back to the first day of classes where we talked about the day in the life of a web request. And now we have mentioned all of these protocols that, were in the alphabet soup and maybe you didn't understand as well when I first talked about this. So go back and review those, and it will be a very, very nice way to put everything back together. And now, is this the end or just the beginning of a journey? So we did complete the journey of this class, of the computer and network security class, on down the protocol stack. However, there's so many other things to review. We did not review in detail all the protocols in every layer. And so for these, you should take a networks class. If you want to learn more about layer 5 and peer-to-peer and mail protocols, if you want to learn more about TCPs, finite state machines, and how they were created step by step, about TCP congestion control, retransmission, socket programming, and actually do some socket programming, take the networking class. And if you want to learn about layer 3, switching mechanisms, SDN, routing, again, the networking class. This class is CSCI 440, and it is offered every odd year's fall. So it was offered on fall 2017. So next time I will offer it, it will be fall 2019. So I hope I will see you in this class where we will be doing a lot of Wireshark, a lot of socket programming, and we will be drilling into a lot of details about all of these protocols and where they came from. As I have said before, if you want to be a successful information security professional, there's two things that you need to know besides security. Actually, it's better to know these two things than security as an undergraduate that has just graduated. So these two things are operating systems, which is a mandatory class that you all take, and computer networks.